if a slinky is dropped, will the bottom fall first? Will the top fall first? Will it fall stretched out? Or will the top and bottom approach each other and then fall? So the result of this problem is that the top will fall first, and it is modeled correctly, showing this happens in my computational model. So I chose this problem because when I was looking at the video of the ideas, when I was looking at the falling slinky video, I thought it was really, really amazing that you could see in slow motion how the bottom completely stays still and the top reaches it. Because it's one of those things where I wouldn't have thought that would happen, but then you think about the physics that goes into it, and it totally makes sense. And just understanding all of the things about forces and tension forces and gravitational forces, you understand why the bottom stays still. So I'll show you quickly in the video how the slow motion, how the slinky works. So it's all stretched out and it reaches the bottom. Then you can see right here how the bottom completely stays still and the top reaches it. And then it falls together. So I took a video of this and I put it into my tracker, and you can see here, this is the x-axis, this is the y, I just switched it. This is the origin, and I put the calibration stick right here, and then I just measured exactly, as time went on, I measured exactly where the top of the slinky was as the slinky fell, like this, so you can see the different points, and here's my graph. And the total time was 0.267 seconds. And here's all the y coordinates. So yeah, so I put all this information into my model. And I used a ball for each different spring just kind of to model it. And you can see that each ball will have a tension force and a gravitational force. And as the tension forces don't equal the gravitational forces anymore, you'll see that the balls will go down, and then they'll fall together. So you can see how this models the fallen slinky. And just looking at the principle of it, you can see spring forces have gravitational and tension forces. And according to the momentum principle, you have the change of momentum equals the net force times the change in time. And that net force equals the tension force minus the gravitational force. Gravitational force is the mass times the times 9.8 times the constant. And then the force of tension is the force going upward in each spring, and then the gravitational force is holding it down. So if you have a constant motion where the spring's just sitting there, the force of tension is going to equal the gravitational force because it's not moving downward, it's just staying there. But if you wanted the slinky to fall, the tension forces must stop equaling the gravitational force. So this force must stop equaling completely the downward force. So each spring in the slinky must stop having tension before it can act on its gravitational force and fall. So you can pretty much understand that, like in the spring that we saw in the video, how the bottom stayed still because the tension force still equaled the gravitational force. And then once the tension force wasn't there anymore, it fell because it fell according to gravity. So yeah, that's my video, and you can see how my computational model modeled the actual slinky in the video.